Are you good for coffee?
Okay, I'll give folks just a little bit longer to trickle in. I see about 24 in the chat, which is low for a Wednesday, but we'll see. It's getting near the end of the term. People have things to do. It's not exactly a beautiful day outside, but you know, you do you. So I guess I should say before I get started, does anybody have any questions? Anything they want to ask about? Comments, observations on life?
Chuck, are you going to hold lab on Monday? Have you decided on that?
Oh yeah, I think I'm just gonna go ahead and push the homework, this one back a week. I mean, turn it in early if you want. I think I'll just push it back a week and just do a lab the following Monday, because really time has no meaning. And if people want to turn it in earlier, they have the capability to do so without the lab. Otherwise, I'd like to be able to do the lab. It's just, yeah. I don't want to force people to come in on some off time or anything like that. And it is technically a day off, so I shouldn't be teaching anything.
Cool, thanks, appreciate it.
And yes, I would like to optimize Zoom. The problem with optimizing anything using R is that that is a good way to make it much slower rather than much faster on account of R not being a very fast platform for things. If I was going to optimize something, I'd go straight to the old C++ and then probably want to die as a result of that. But, you know, be a way to do something fast. Okay, I'll go ahead and get started here, about 28-ish. Okay, so today's lecture is on strings, on text data. So we're going to cover today something that I feel is really important and usually neglected in other R classes. If you're taking, if you learn R through like statistics classes, method sequences and stuff like that, they will usually teach you nothing about dealing with text data because they kind of assume you're going to be working with statistical models. It's like, oh, it's all numeric, and if it's categorical, you should just recode it as dummy variables and throw it in, right? The reality is most of us are actually probably going to work with a lot of text data and need to do things with it. Some of us are going to work with extreme amounts where their primary data they work with is sentences and paragraphs. Maybe they work with Twitter posts and stuff like that. You need to know a lot of things additional to manipulate these things effectively that you will not get almost anywhere else. And it's kind of like very troubling you don't learn these things, including one big thing, regular expressions, which isn't unique to R and is sort of universally used across programming languages. And we'll spend most of today talking about those. Okay. So the data I'm going to use for examples today is real live King County food safety inspection data. So these data you can pull right from data.kingcounty.gov. They describe all of the health violations that restaurants have had when they've had inspectors go to visit them. They're live updated and everything like that. So this is kind of a fun data set because it lets us explore all of the places that are going to poison us if we eat there. Not that most of us are eating at those places now, but you know, maybe the places you're getting takeout from will kill you. Okay, so these data are kind of big. This is the kind of data set that I would say you probably want to save them and load them from a local directory rather than pull them from the website every time. But it is hosted on GitHub here, and you can pull the CSV down like this. It's their bandwidth, not mine. So, feel free to download from them to your heart's content, but it might take it a little bit of a little minute if you're not on a fast internet connection. And if you do it repeatedly, you don't want to be on some limited internet connection. Like I said about like if you're on a mobile phone or something like that, you're going to eat through bandwidth. Okay. So for this data set, it's available on my GitHub here. I've specified the column types manually just to make sure they read in nicely. This is one of those things I like to do with data sets that I've become familiar with. Instead of manually specifying and converting columns afterwards, I just load the data in originally and specify them. And this basically says it's character, 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 2 numerics, some character, integer, and capital D as a date at the end. I've just manually specified and said these are what the columns are. You'd have to change this if the data got updated and they added another column or something, which is a thing that happens in administrative data all the damn time. They just randomly add a new column because they want to recategorize something or whatever. Anyway, so this is what these data look like, okay? So it's a moderately large data set. It's only 258,000 rows, 23 columns. So this is the kind of data set that your computer doesn't think is big, but is large enough that you can't like browse through it very easily with the view command. So it has a lot of different measures in here, and it's clearly administrative data because of the things it has in here. You can see it has the name of the restaurant. It has an identifier for that restaurant. It has the dates of inspections, descriptions of the restaurants. It has their addresses, what city they're in, the zip code, phone numbers, exact latitude and longitude, which we're going to use in the mapping lecture next week. And a bunch of other stuff. The important ones being the inspection score. The inspection score is essentially the number of violations they found in that last inspection. So 10 points means a lot of violations occurred, 15 points, and so on, right? We're going to be mostly focusing on places that had a really high inspection score. That is, they had a lot of violations. If you wanted to use this data for someone to dig into it, you can get the exact violations that happened, like non-food contact surfaces not clean. Maybe they didn't have IDs on their shellfish, that kind of stuff, right? It's a lot of interesting violations. Okay. And then, of course, there's a date. Okay. So strings, what we're going to be talking about today. So a general programming term for a unit of character data is a string, and a string just means a sequence of characters. When you work in R and you see stuff written for R, the terms strings and character data are mostly interchangeable, okay? A string is just usually a single unit of it. So a vector of strings, that would be a character column in your data set, is a bunch of strings. In other languages other than R, strings will more often refer to something like a sequence of numeric information. Commonly, you might see binary strings like this. It's a sequence of zeros and ones. We rarely directly use numeric strings like this in R, except in the case of logical vectors. Logical vectors, trues and falses, are really a binary string like that. Okay. So the thing to note about strings is that even if they are numbers, they are sequences of numbers. They are not single numbers. This is what makes them a string, that they are a sequence, the order of them matters, and they're not conveying typically numeric information. They're conveying something about the location, as in this value is 0, this value is 1. That doesn't necessarily mean these two are related in some like strong way. One of the key things that separates a string from an actual number, for instance, is leading zeros are actually meaningful, right? In R, if you have a leading 0 in a numeric vector, it cuts the leading zeros off because a leading 0 doesn't mean anything in a number, right? It's just a blank space, basically. In a string, 0, 1 is not the same as 1, okay? So this sort of defines the difference between a string and a number. If you're in a case where your leading zeros matter, you're working with string data, not numeric data. Okay. Does anyone have any questions about those basics? Yeah, it's just text data. Okay. So basics about strings in R. So some of this is review because we've been playing with string a fair amount throughout the term. So we've seen the n character function, nchar. This gets the number of characters in a string or a vector of string. So for instance, if I had a data set like this and I wanted to make sure my zip codes were the right type of zip codes, that is 5-digit and not like 10-digit zip codes, I might do something like this. I take my restaurant's data and then I mutate a new column, which is zip length. It's equal to the number of characters in the zip code column. And then I just count the zip lengths. And we see 258,629 of these places have a 5-digit zip code, and one of them has a 10-digit zip code. Okay, so if this was a higher number, like lots of them, you might want to, do some of it. In this case, I am going to change it and get rid of it, but this is basically one observation with an improper number. So you can use n character like this to sort of do a check on a column to make sure it meets your expectations. If you're expecting zip codes and they expect them to be 5 digits, you should check to make sure they're all 5 digits. The one that's not 5 digits, it might be that it's its full 10-digit zip code, but it might also be something like your data loaded incorrectly. Maybe it compressed in some of the adjacent column into this column. You might have to adjust something in the way your data are read in. Okay, simple data quality check. So substring is another function we've used, which you should be familiar with because we've used it in homeworks, we've used it in multiple labs. We could use this to pull out just the first 5 digits of the zip code, right? So what I want to do is I want to overwrite my restaurant's data. With my restaurant's data, I'm going to mutate a new zip5 column. This is going to be a 5-digit only zip code. Really, I'm only modifying one value in here because there's only one 10-digit one, but the example works regardless of how many there are. I'm going to say the 5-digit zip code is equal to a substring of zip code where we start at the first character, we finish at the 5th. Anything that is not between value 1 and 5 inclusive will be dropped from the string. So this will pull out that first 5 digits of zip code, okay? I then say restaurants, distinct zip code head, just to see that they're all 5-digit zip codes. I didn't butcher anything, right? Okay, familiar with substring? Nothing too scary there yet? Okay. Paste is something we've used a whole bunch in this class, right? You can combine parts of strings together using paste. So for instance, something you might want to do, say you're working with these restaurants' data, but what you actually need out of them is the mailing address for these restaurants, right? There's a variety of reasons you might want something like this. Maybe you're actually preparing mailers or something. So I did this for a sort of survey-based project where we needed to construct mailing addresses out of data where we had all these different pieces of information in discrete columns. You can just paste them together and assemble a mailing address. So we could do that like this. We're going to add to our restaurant's data frame a new column called mailing address. For this, I'm just going to say, I want to paste together the street address, comma space, the city, comma space, the zip code, and I want to separate it with nothing. If you do separator equals nothing like this, it's just quotes with nothing in between them. This is the same as paste 0, which I've used a bunch in lab, if you remember that. This basically just says, take for each individual row of the data, take the address column and then stick it together with all these other things. So it's just going to have the street address, for instance, 2920 Southwest Avalon Way is the address for the first restaurant. Then space period, or not space period, but comma space. Then the city is Seattle, comma space, Washington, and then the zip code 98126. So this takes data from 3 different columns and stitches it together into a full mailing address using paste. Okay, does that make sense? It's a useful operation you might want to do in a number of other cases. It's also something useful for like stitching together people's names if you have data sets with actual names or places, all kinds of stuff. I do this all the time. It's also another thing you might commonly want to do if, say, you have 2 different IDs and both of them are required to uniquely identify an observation. You could actually just paste them together either as one unit or like put a dash between them, and then you have a single column that contains all that identifying information. Okay, this is common if you have sort of like data that has like an individual ID nested in a household or nested in a city or something like that, but you have to uniquely identify them with every column. Put them all together into one ID. You can just paste it. Okay. So paste 0, like I've said before many times, is just a shortcut for paste without any separator, right? If I say paste the numbers 1 through 5 and the first 5 letters of the English alphabet, I will get 1 space A, 2 space B, 3 space C, and so on, because by default, paste separates the stuff here and the stuff here with a space, right? If I don't want it to do that, I can say paste these same things, separator equals nothing, it gets rid of the spaces, or I can do the even lazier option, which is paste 0, and it just by default doesn't have the spaces in it. Okay, so that's the relationship between this. Paste 0 is just paste with separator equals nothing. That's all it's doing. Okay, so paste has another option to it, which you may have seen me use in a lab earlier in this term, and I think I actually may have used it once in a lecture. Okay, so separator we've seen, and that controls what happens when you do what I call entry-wise squishing of vectors. So if you've got a vector here with 4 observations and a vector here with 4 observations, paste just sticks them together into one vector that still has 4 observations, okay? What collapse does, the next argument to paste, is it will convert things that go into it from a vector of multiple observations to a single string, right? So here's some examples of how that works. If I say paste the first 5 letters together and collapse equals exclamation point, it makes, instead of getting 5 observations out, that is a length 5 vector, the A, B, C, D, and E all get collapsed down into a single element of a vector, and then the thing I say collapse on goes between them. Okay, so if you have a whole bunch of things in a single vector that you want to collapse into one observation, you use collapse. Okay, contrast this with paste 1 to 5, letters 1 through 5, separator plus. This stays length 5. There's 5 individual elements in this vector, and within each one, the things in part of this vector and the part of this vector are separated by a plus, right? Collapse reduces it to 1 element. Paste does not. If I do collapse here with 2 things, 1 to 5 and letters 1 to 5, and I collapse on this, you'll see it pastes the first thing to the second thing, that is 1 and A, and then does the thing we collapse on, and then 2B, collapse thing, 3C. So it pastes them together and then collapses the results together from it. Okay? Then I might say something like, well, we've seen this. If I say paste 1 through 5 and a single letter and the separator is this Z over here will be recycled to be length 5. So we get 1 times Z, 2 times Z, 3 times Z, and so on. And then I can mix this all together and say, let's paste the numbers 1 through 5 to Z with a separator of asterisk and then collapse on this. And you'll see I get 1 times Z like I had above. But then the collapse thing comes in between them, and they all get stitched together into a single observation of 1 character vector, okay? So this is sort of one of those things where you might not use all this functionality, but every once in a while you might come up with reasons that you want to stitch together lots of different character vectors in special configurations. One of the most common applications for this is if you want to construct formulas for a lot of models in an algorithmic fashion. So maybe you need to run like 100 models and they all have different sets of parameters. About last year, I actually helped somebody set something up like this. They were doing a special type of cross-validation on like 80 different nested models. They didn't want to have to manually type every single one of the models. We just showed them how with a couple combinations of paste with different separators and collapses, we could use about 4 lines of code to construct all 80 of the models they were working with. Beats doing it manually. Okay. Fun stuff. So the main thing I want to talk about today is the stringr package. And I've been rewatching The Wire recently, so I had to introduce this. If you're not familiar, just let Idris Elba go. But if not, this is a funny joke. Anyway, the stringr package is a tidyverse package for string manipulation. So it's part of the tidyverse with ggplot, dplyr, tidyr, lubridate, reader, and all that. But what stringr does is it provides functions specifically for manipulating strings, categorical data, right? So it makes all the things you could normally do with base R, like pasting, doing the n character function, substring, and all that. It makes those easier with its own versions of those functions that have better error messages, better error handling, things like that, some additional functionality. It also has some functions in it which do entirely new things which, well, you can do in base R in roundabout ways, are kind of a pain. Things like removing white space or padding it out, that is adding characters when you want things to be a specific width, common with zip codes. You want to put those leading zeros back in if they got read in as numeric, and also perform tasks, and this is the big one, related to pattern matching. That is detecting, locating, extracting, matching, replacing, and splitting parts of strings, right? So this is a common sort of thing. Maybe you want to convert an abbreviation to a full word or vice versa. Maybe you want to find which observations have particular sets of letters in them, that kind of thing, right? These functions will use regular expressions to describe the patterns you want to search for. And I'm going to talk a bunch about regular expressions. There are base R and also the stringy package versions for using this sort of pattern matching, but they're harder to use, harder to remember. They have arcane syntax. The stringr ones tend to be really easy to use, and considering regular expressions themselves are already sort of hard to use, you try to make, you should try to make things as easy as possible. Use these stringr ones and then let the difficulty be in writing the regular expressions, which, as you'll see in a bit, can be kind of hard to put together. One really nice thing about the stringr package that a bunch of packages, especially in the tidyverse, have started doing is almost all the functions in it begin with str underscore. This means if you can't remember the exact function you want to use in stringr, you can start typing str underscore, hit tab, and the only functions listed are going to be ones from the stringr package. So autocomplete in RStudio combined with some careful sort of design of the names of functions makes it really easy to use this package. Another package we're going to use next week, the SF package, also does this where all its functions begin with ST. I really like it when packages do this. It sets off all the functions separate from everything else. Makes it easy to find things. Okay, so for this, we could just load up the stringr package. If you've installed the tidyverse, you have it already. It's part of it. And in fact, if you just do library tidyverse, it loads stringr. It's one of the core packages. Okay, so stringr has a bunch of functions in it which are equivalent to base R1s, but maybe have a little extra functionality. So you may have seen me use string underscore sub instead of substring. It's a very similar function. The difference between string sub and substring is that it will take negative numbers for indexing the locations of a string. This is something really handy. So maybe what I want is, I want to get a substring of Washington or states in general, but for some reason I really just don't like the last two letters of these state names. So I can say, let's take a string sub of Washington, start at the first letter, but finish 3 from the end. So this says go from 1 to, not this one, this is 1 back, 2 back, 3 back. So it's going to include the third back one to the beginning. So string sub 1 to 3 gives me Washington, if I wanted that for some particular reason. Okay? Negative indexing is really nice. For instance, if you want to do something like cut off like .csv at the end of a CSV file's file name, right? I can just say -4 and it will cut off .csv. Okay, so we use this in the homework lab. Okay, handy. String underscore C, string combine, works exactly like paste, except its default separator is blank, like paste 0. So if I say string C and paste together these letters and these numbers, by default, it gives me A1, B2, C3, D4, E5. But so this looks like paste 0. Unlike paste 0, I could add another argument, separator equals, and then it will actually give it a separator. So this manages to do both the things that paste and paste 0 do. So theoretically, you could replace paste with this entirely. I don't, mainly because I forget to all the time, and paste is a base R function that I want you to know how to use and just understand. But technically speaking, you could fully replace paste with this and you wouldn't miss anything. Okay, so there's other equivalencies. string length is equivalent to n character. So if I want to know how many letters there are in the word weasels, there are 7. N character says that there are 7. String length also says there are 7. This is essentially an alias for n character. It does the exact same thing. Sometimes they like to have aliases that is something that does the exact same thing as a base function in a package, because they might do something like handle NAs or produce better error messages, that kind of thing. I don't actually know what advantage string length has over n character. It's even more stuff to type, but it's there, you can use it. Okay, so some other useful functions in stringr are string to upper, string to lower, and string to title, among other ones. These are conversion functions. What they will do is you give them text strings, and they will convert them to all uppercase, all lowercase, title case. There's also sentence case and some other ones, okay? This is something I really like to do at the very early stages of data cleaning and manipulating a data set. I like to, unless the capitals and lower cases convey important information, like there are like ID codes and some sort of hash that uppercase, lowercase matters, I like to convert everything to either uppercase or lowercase to get rid of duplicates, things like this. If you look in the restaurants data at cities, they have lowercase Seattle and uppercase Seattle, lowercase Issaquah, and you can't see it, but there's an uppercase Issaquah, okay? So Seattle and Seattle are the same Seattle, but to R, they are not. R thinks this and this are different things. So to prevent that from happening, I might want to say, to my restaurants data, replace it with restaurants data where I've taken the names, the addresses, and the cities, and I've converted all of those variables to uppercase. Okay? So mutate add is just saying, take all these variables, do this thing over there to them. And now you can see Seattle, Kent, Bellevue, Issaquah, whatever, there aren't any lowercase versions of these hanging around. They're all uppercase now, so I've essentially like unified these things. So here was a question over here I saw pop up a second ago. Can you do a mean string length? Like, what is the average length of all strings in a column? You absolutely can. So string length produces a numeric value, and so you can take a mean of it if you wanted to know that. That might be something useful if the number of characters in it is meaningful in some way. For instance, you might be doing something like working with Twitter data. If each individual observation is a full tweet, you might be interested in what is the length, the mean length in characters in tweets, right? You know, something of interest. But yeah, you absolutely can. Okay. So another function that's useful in stringr is string trim. So it's common if you have human entered text data to have extra spaces at the beginning or ends of things that might cause you problems. So for instance, the first observation in our data set here at the Shack LLC has a hanging space right here. This space isn't supposed to be there probably. The name probably does not literally have a hanging space in it. It would be an odd and fun troll move to own a business and demand to include your hanging or leading space in the name, but that's probably not reality, okay? So we might want to get rid of these leading or trailing spaces, especially because if there's multiple observations, if it was hand entered, maybe some of them have that space and some don't, and we don't want to be treated as different observations, okay? So any character column in these administrative data might be affected. I kind of consider like these human entering things in data administrative data to be sort of like glitter or herpes. If there's in one particular column, they're probably fucking everywhere inside those data, right? So you might just want to inoculate every column in the data set in this way. Fix it all in one go before you start doing work on it, right? So what I'm going to do is I'm just going to string trim every character column in the data set. So I'm going to say, take my restaurants data, mutate if. If a column is character data, string trim it. Okay, so what this is going to do is go and find every character column in our data set, apply this function to it, and overwrite that column with the trimmed version. Okay, now we can see at the Shack LLC no longer has a space, and in addition, every other character column in our data set has had this problem solved. There's also another version of this, which I'll mention briefly very at the end, called string squish. String squish removes the trailing and leading spaces, but it also removes all double spaces inside strings. It'll leave a single space alone, but if there's two sequential spaces, it will reduce them to one space. So this would be a really good way to process, say you have an advisor like I do who insists in having two spaces after every period in your document, and you don't like that in your markdown document, you just string squish the whole document and your problem is solved. Okay. So here's a question here. I think I might have missed this, but can the stringr functions also be applied to factor vectors, or should the vector type be character? You can apply them to factor vectors, but you're going to have to convert them to character first. Because factors have an underlying numeric representation. So the value of any given factor entry is an integer like 1, 2, 3, and 4. It might behave a little weirdly if you work directly on it with stringr. In fact, it's most likely going to be like, I need character data, not factor, or it's just going to coerce it to character data and then do it. Okay, so normally a factor is something I consider to be or treat like an end product. Everything I work in character until right before I'm going to use it for something, then I'll convert it to factor and do things like arrange the levels and stuff. But I say leave conversion to factor until the very end of whatever process you're doing. Factor is mostly just to get things ordered the way you want in a plot or in a model. Okay, so we've gone ahead and done this. Yeah, and so we've taken care of capitals and lower cases by making everything caps. We've got rid of leading and trailing spaces. Okay, so now I want to move on to a big topic in the general world of data sort of programming, which is regular expressions and pattern matching. Before I start this, does anyone have any questions about this prior content? Because this is, well, we'll still be using the stringr package. It's a slight change in pace. Okay, let's get into our foray. So this is the tougher part of the lecture, but it's also probably one of the most useful things you could possibly get out of this class if you work at all ever with categorical data. Okay, so what are regular expressions? Regular expressions, or regexes, are how we describe patterns we're looking for in text in a way that a computer can understand. The idea is we will write an expression, apply it to some string input, and then we can do stuff with the matches it finds. Okay? So regexes consist of two components. They consist of literal characters. Literal characters are the things we want to search for, like literally. This is exactly what we want to find. Maybe we want to find Seattle with SEA, which is what we did in the part 1 of homework 5. We want to find all the Seattle precincts. We were looking for SEA. You didn't realize it when you did it, but you were using regular expressions to search in that thing we did before. Anyway, so you could search for SEA, or maybe you want 206 area code. So you search for 206, okay? So that's straightforward. I want to find SEA, so I search for SEA. The other type of thing in regular expressions, and the complicated part of it, comes in what are called meta characters. Meta characters are things that allow us to be flexible in describing the patterns we're searching for. A lot of different special characters in that you might write, different pieces of punctuation, are meta characters in regular expressions. Things like backslashes, carets, dollar signs, periods, pipes, question marks, different types of brackets are all meta characters that all have a different meaning in your regular expressions. If you are in a case where you want to search for this literal character, like a squiggly bracket or a parenthesis, you have to specifically tell R and tell the regular expression that you're searching for this character and not using it as a meta character. To do that, what you have to do is something called escaping the character. To escape the character, that is to treat it as a literal character, you need to put 2 backslashes in front of it. So if what you're searching for is parenthesis 206 parenthesis literally, to search for that, you actually need to search for backslash backslash parenthesis 206 backslash backslash parenthesis. These backslashes say, I want the actual parenthesis, not this parenthesis meta character. And we're going to get to see what the parenthesis meta character does in a little bit to see why you might not want to be searching for literal parentheses. Okay. So here's a question here. I've been working a lot with long format public comments and surveys. Is there an expression we could create that searches for any terms that occur more than X times and then arranges by frequency, similar but less painfully than Excel will? Yes, you absolutely can, but it's not so much a regular expression that you're going to do that. Instead, I would recommend using like the tidy text package. Take each individual public comment, divide it up into individual words. You might consider stemming them, that is removing their sort of suffixes and stuff. And then you'd essentially count each unique word, find the most frequent ones and arrange them by frequency. It's about 2 lines of code in tidy text to do that. So very trivial to do, but it's not exactly regular expressions. It's more text manipulation type stuff. Really what you do is imagine that if you had a single observation that was like a paragraph, imagine that you convert that paragraph into a vector where every word is an element in the vector, and then you can just count the number of those words in the vector using basically count or unique, right? Very easy to do, and tidy text is sort of the modern way most people do it in text analytics. Which the great thing is, tidy text has a excellent textbook, which is available for free online. We'll just search for tidy text textbook. It's excellent. It walks you through everything for text analysis. It's pretty great. Okay. Used to teach a lecture on it, but I'm so out of date on text analysis that I just gave up. I have some wreckage of a lecture still posted on the website, but it's pretty out of date. Okay, next one. So the first function I want to use and demonstrate with regular expressions is the string detect function, okay? What string detect does is you give it a character vector you want to search through, and then you give it a regular expression. Anytime it finds a row that matches the regular expression, whatever you're searching for, string detect returns a true. If it does not find the text you're looking for, it returns a false. Because it returns trues and falses, it's really good for using in the filter command, because what filter does is subset your data where it keeps the trues and discards the falses. I use string detect all the time to sort out and filter through data by hunting through terms, okay? So in this particular example, what I want to do is I want to get the inspections, the food safety inspections specifically for coffee shops, okay? What I do here is I'm just going to say a coffee shop is anything that has in its name coffee, espresso, or roaster. You could theoretically introduce things like cafe or something like that, but there's a lot of cafes that are really restaurants. You know, you can come up with your own thing. Okay, so the regex for this is just coffee or espresso or roaster. The reason for this is that pipe, much the same way in like filter commands and stuff, is a meta character that means or. If it finds any one of these things, it's going to return a true, okay? So what I say here is I'm going to subset my data to coffee, which is from my restaurant's data, filtered down to cases only where string detect in the name of the restaurant finds coffee or espresso or roaster. You'll notice the thing with regular expressions, the entire expression is a single string, okay? So no matter how much stuff I put in this regular expression, it will be a single string and not a vector of strings, okay? So I've just said I want coffee or espresso or roaster. If I take my coffee data, get distinct restaurants and look at the head, we see we've gotten kind of what we're after. I've got Two Sisters Espresso, 701 Coffee, 909 Coffee and Wine, Alki Homefront Smoothies and Espresso, so on and so forth, right? So I've subset my data down to only these things containing this. And there's an excellent question right here in chat. Would this find roastery with a Y? The answer is yes. So the way the regular expressions work is they're not looking specifically for words or anything, they're looking for the entirety of the text. So roastery with a Y still contains roaster, so it will return a true. If we wanted to get roaster but not roastery, we could add a space here at the end and it would search for roaster ending in a space. But then if it was the end of the string, we wouldn't capture it. We'll show some special cases on how to deal with spaces and stuff in one of the next examples. Okay, So here, you've said string detect is similar to grepl. Is there any difference between string detect and grepl that we should know about? Not really. I think grepl orders its arguments slightly differently, and the error messages for grepl are probably inscrutable, but string detect is basically doing the same thing as grepl, and you could actually use grepl here instead of string detect, rearrange its arguments, and get the same result. Grepl is logical grep, and yeah, it'll basically do the same thing. So if you're familiar with and used to using grep and grepl and the sort of general grep family of things, everything with stringr like this is going to look pretty familiar, but the syntax is a little bit more uniform and the help files are better with the stringr ones. I still occasionally use grepl because it's the first thing that pops into my mind because I have a little bit of a Unix background. Okay, not a good one though. I'm terrible at shell scripting nowadays. Anyway, so yeah, any questions about how we found that, how that works? We will keep escalating our regular expressions, which is the usual format for my class. Escalate until everyone is uncomfortable with what I'm doing. Okay, here we go. So maybe what we want to know is the coffee that I drink going to kill me, just maybe on average, right? So you'd think coffee shops, being that they primarily serve coffee, maybe some pastries and stuff, would have a really hard time racking up lots of health code violations. Somehow, some of them manage to do it. So what I want to do here is get just unique business identifiers, keep their most recent inspection score, and then just pull a histogram of it. So I say, get my coffee data, select only the things I care about, which are the business ID, the name of the restaurant, the inspection score, and the date. I'm going to group it by the business IDs and filter so date is equal to the max date within the business ID. So this says basically, give me the most recent inspection only. Then I want distinct observations in case there's duplicate rows. Turns out there sometimes are duplicate rows with the exact same info. And then I just plot it where my AES is the inspection score, huck it into a histogram, and here's what I get. So you see, most recent inspection scores for Seattle coffee shops are typically a 0. A 0 means there were no health code violations. That's good. If you only make coffee, you shouldn't be able to make too many violations, right? But somehow, look at this tail. Somehow in this far right tail, there's up to 40 health code violations in some of these coffee shops out there, right? 40. It's not like they've got shellfish or something like that. How do you get 40 health code violations in a coffee shop or something like that? In next week's lecture on mapping, we're actually going to find the geographical locations of some of these, or actually maybe that's the homework data. We'll find the geographical locations of these. The homework are fun. You can see what locations in like certain areas of Seattle will poison you. Be fun when we find that. Okay, so some coffee shops will probably kill me. Okay, so string detect can be used in slightly more advanced ways than just searching for this thing or this thing or this thing. So maybe we want something like finding all the phone numbers whose first 3 digits are 206. Which sounds easy, but there's some complexity to it, right? The thing is sometimes the phone numbers will have parentheses around them, and we also only want to get 206s that occur at the beginning of a phone number. I don't want to get 555-206 something. I only want things that begin in 206, whether or not they have parentheses around them, okay? So I'm going to use this regular expression, which I'm going to explain after I show this result here. The regular expression is caret is the little exponential type sign, // parenthesis, question mark, 206. Then what I do, and this is a thing I recommend doing if you're working with regular expressions, create a bunch of test examples, just a minimum set of them that you know should return certain like values for your search. So in this case, I know this begins in 206, so it should return a true in my string detect. This begins with 206 in parentheses, so it should return a true if my expression works. So should this, but 555-206 should return a false because the 206 is not at the start. So this gives me a base sort of ground test I can test my expression with. And I can see here, if I say string detect, my phone test examples, and the pattern I used, I get true for the first 3 like I expect and false for the last, so I know it worked. But how did it work? So what I have here, right, is I have caret comes first. Caret is a meta character in regular expressions. This says start looking at the beginning of the string. So if you start looking at the beginning of the string, it means whatever comes immediately after it is going to need to be the very first thing in the string. This is how we tell it we're going to look at the start of the phone number and not at the end. Normally, a regular expression is happy matching anywhere in it. If you begin with this caret here, it has to match at the start, which is what we want for 206 numbers, right? Then I say backslash, backslash, parenthesis, question mark. This is actually basically one search term. This says I'm looking for a left parenthesis. Because the parenthesis is a meta character, I do 2 slashes so I get the actual parenthesis, but then I put a question mark after it. In regular expressions, a question mark means whatever single thing precedes the question mark is optional. So it can be there, but it doesn't have to be. So this allows us to match a parenthesis at the start or no parenthesis at the start, but no other character is accepted at the start other than 206. Then 206 here is a literal string to look for after that optional parenthesis. So by our logic here, what we're looking for is a string that begins with either a parenthesis and then 206 or just 206 and nothing else is okay. Does that make sense? And it appears to work. I can then, do I apply it? Okay, I will. Another thing you might want to use, so let's say you have a whole bunch of text data in your R and you want a visual representation of the matches your regular expression makes. There is a stringr view function called str_view. I don't run this here because I can't have my lecture slides pop up an actual window, but what string view does is it will pop open a window, much like the viewer window in our studio, and it will show highlighted all of the pieces of text in whatever thing you give to it that match whatever pattern you give it. So if you want to know what parts of the text you're actually matching with a regular expression, this gives you a visual representation of it. Be careful though, this generates a little web page in the viewer pane when you do it. If you give it a really long vector or something here, like 100,000 observations or something, it's still going to try and generate a web page with 100,000 observations highlighted, and it's going to make your RStudio grind to a crawl and possibly die. So usually work with a subset or a sample if you use string view, but this is a handy dandy way to see what your regular expression is selecting. Another thing I would recommend doing is there's some great what you see is what you get regular expression tools online. One of them is linked off of the website. So if I pop open to the website for the class, go down to week 8, there is a site for regular expression testing, which allows you to type in your regular expressions as you go, and it shows what text is being highlighted by the particular regular expression you're working with, right? So if I start deleting things, you'll see the things start disappearing and what it's highlighting, and it gives you errors if it's an invalid regular expression. This is another thing, if you have some complex thing you're searching for, you might just want to go test it out on the website rather than kind of beat your face against it. Okay. Anyway. So, is there a meta character like caret that specifies the end of the string? Yes, $, and we're going to use it in a little bit. Caret is the beginning of the string, $, is the end. Okay. So, let's find out how many 206 numbers there are in my data. So I can say, take my restaurant's data, mutate a new variable that has a 206 number, which is just the result of string detect on their phone number using my 206 pattern. I'm then going to group by has a 206 number and tally it. This is the same as doing count has 206 number. And what we see here is 66,000 or so don't have 206 numbers. About 110,000 do have 206 numbers. And then about 83,000 return an NA. We get an NA if they don't have a phone number. String detect cannot do a search for something if there is nothing to search inside of. If there's an NA observation for phone, it just returns an NA, kind of like how if else run on it returns an NA if it's an NA you're testing against. Okay. So we know how many 206 numbers there are if for some reason that's something we were interested in. A lot of examples today are examples of if you were somehow interested in this. Okay. So next, we know how to do things, find things with trues and falses. Oh, so here's a question. Why do you have group by before you tally? So if I don't group on something and I tally, it's just going to return to me the number of observations in my data set. What tally does is tally counts the number of observations in your current group. If you don't group your data, every observation in your data frame is in the same group. I could instead use count has 206 number instead of both of those, but sometimes I like to switch it up and show tally and group by. Most cases, there's no reason to use group by and then tally unless you're using special options inside tally. But when I wrote this, this was just the first thing I thought to do, which is funny because I almost never use tally. But yeah, identical result. Okay, so something else you might want to do. So it's relatively simple to get trues and falses and use them for filtering or counting or something. Maybe what we want to do is not get trues and falses, but we want to make some matches and extract the thing that we match from the text. Okay, so in this case, what I want to do is I want to find out in general terms where most of the restaurants are in Seattle. A convenient way to do that is to extract the directional parts of the addresses in Seattle. So if you know Seattle relatively well, you've either noticed or just real aware of the fact that Seattle is broken up into a semi-quadrant system for addresses. Every address that has a north in it is in a very specific area of Seattle. It's in the space in between, it's like where First Street starts just to the side of I-5 if you're in the north side, all the way like out is actually what, that's north, northeast is just on the other side of First Street. So on, right? You're in like these specific blocks, right? If you know the address you're at, like I'm at Northeast 54th Street, you know exactly what part of the city you're in, okay? So I want to find out where all the restaurants are at. What I'm going to do is I'm going to look for a particular direction pattern in the addresses. So the idea here is I'm going to provide some examples to show what I want to extract from them. If I have an address like 2812 Thorndike Avenue West, the only directional in here, the thing I want to extract is the west right here, and I want to discard all this over here. I just care about the west. If I get 512 Northwest 65th Street, I want the northwest and not the rest of it. If something is 407 Cedar Street, it doesn't have a directional because it's in the middle of the city. Things in the middle of the city get no directional, so I want this to return nothing, like an NA. And then over here, 15 Nickerson Street, same thing. But notice the complexity in doing this. I want to get west, northwest, I want to get north, but I don't want to get the N in Nickerson Street, the S in street over here for south and that kind of stuff. I want to get these directionals like this without pulling random letters out of my street names, okay? The thing is I can look at this and logically come up with some rules that determine what is the directional and what is not the address. So you'll notice here the directionals always pretty much have a space before them, right? None of these directionals, nothing begins with, doesn't have a street number, just says like West Thorndike Avenue. All these addresses have a street number, which means all of them have a space before the directional. Sometimes though, they will have a space, the directional, and a space here. But if they don't have a space after them, they always are at the end. So I don't want to get space N and then get the I here in Nickerson. I want to get like space northwest space or space west end of string. So you see how I came up with those logical rules? There's not like a special like magical system to this. I just eyeball the data and come up with logic that will determine how I can find what I want. And I poke at the regular expression until it does what I want it to do. So it's an iterative process, like most other things in data analysis. So the pattern that I come up with to do this is space, every possible directional separated by pipes, which is basically ors, and then space or $sign. Let's break down what this is. So the first space in here is a literal space. It means that we will only match things that begin with a space. So this rules out any text like the N in the middle of Thorndike because it doesn't have a space before it. Next, this whole block here is what is referred to as a group. What parentheses do in regular expressions is they set aside something as a group so that it evaluates the entire expression in here on its own. Kind of like if you put a bunch of R syntax in parentheses, it runs all that code in there first, evaluates it, and then you can do things like multiply it or whatever. So parentheses basically operate kind of like they do in math. This just says match one of these things in here, and then that's it, but you got to match one of them in this group before you go and match other stuff in this expression. So this says match either north, northwest, northeast, south, southwest, southeast, west, or east. Got to match one of them. Any one of them will do. Okay. Then we have this other group here. This one says we want to match a space or a dollar sign. And as was asked a minute ago, is there a meta character that says end a string? The answer is dollar sign, right? So this says we will match one of these two things. Either of them is good. We're either okay to match a space that occurs after the directional, or we're okay for the string to end after the directional, which gets things like space W end of string. The dollar sign is the end of the string here, but it also gets space northwest space because we can match either the space or the dollar sign. Does that make sense? Yeah. So let's see how it works. I'm going to take my restaurant's data. I'm going to go down to only the distinct addresses in my data. I'm then going to mutate. So city region is equal to, notice I do string trim here. Do you remember what string trim does? It removes extraneous spaces. If I look back over here, you'll notice the matches. If it matches a space and a W, it keeps the space it matched. Space this. Oh, and I forgot to actually say the function we're using is string extract. What string extract does is instead of returning trues and falses for its matches, it returns the literal text that it got matched to. So if we matched this thing, this address, the thing that matched it was space W, string extract just gives you the space W. The northwest matches here, and notice northwest has space, northwest space. String extract gives you it with the spaces. The thing is, the actual directionals don't have the spaces in them. That's just an extraneous thing from doing the matching. So I use string trim here to cut off those extraneous spaces. What they're going to be cut off from is string extract, the address, the direction pattern from the last slide. I'm then going to count the different city regions and arrange in descending order so we can see where most of the restaurants in the data are. So here we see that there are 2,086 restaurant addresses in Northeast Seattle. This doesn't really come to a surprise to people probably who are natives of Seattle or have spent much time here and realize exactly how large the Northeast Seattle block is and what it contains, right? This is every restaurant running all the way up Lake City Way and all that kind of stuff. And the Northeastern District starts on actually the west side of I-5. It covers an enormous amount of territory. It's everything north of the cut, the canal, and all the way up to the city border. So it's by far the largest area of Seattle. Okay. The next is South Seattle with 1,764. This captures the ID and stuff like this, extending all the way to the southern border of Seattle. NA has 1,745. Well, an NA means there was no directional, so it means there's 1,745 unique addresses in the center of the city. And then so on for north, southeast, southwest, east, northwest, and west. Okay. Any questions about how I did that? Not too bad. So we'll get worse. Okay. So something you might want to do is you don't want to just find patterns. You don't want to just extract them. Maybe you want to find things in your data and replace them using regular expressions. Okay. So here's something I might want to do. Let's say I want to do a street level analysis of inspections. That is, I want to know what streets in the city of Seattle are most likely to poison me if I eat on them regularly, or at least evenly distribute my eating across those streets. Okay. So for instance, I want to compare the Ave to Pike Street and maybe King Street down in South Seattle or something like that, you know, where all the delicious food is. Okay. Something we might need to do that though is the addresses contain both the building numbers and the streets themselves, but we only want the streets. So what I want to do is I want to take those building numbers and remove them from our strings. I just want to get the streets. So I want to replace them with nothing. What I'm going to do is I'm going to use this hideous regular expression, which I'm going to explain on its own entire slide in a minute, to clean up addresses that look like this. I have things like 2812 Thorndike Avenue West. What I want to extract is Thorndike Avenue West. If I have First Avenue, I want to extract all of this, First Avenue. If I have 10A First Avenue, I still want to extract only First Avenue. If I have 10-A First Avenue, I still want to get First Avenue. If I have 5201-B University Way Northeast, I want to keep only University Way Northeast. And if I have, these are real Seattle addresses, if I have something terrible like 7040 and a half 15th Avenue Northwest, I want the 15th Avenue Northwest. What is a half address and why do they do that? Seattle does this all the time. Anyway, so I need to extract those specific things. So I have this expression which I'm going to explain, but you can see it works. Thorndike Avenue West, First Avenue, First Avenue, First Avenue, University Way Northeast, 15th Avenue Northwest. Okay? So, oh, this is great. You lived at a half address. Yeah, I drive and deliver, I bet terrible. It's just, it boggles the mind. It's like, what is a half address? I know it's like sometimes like a unit in one address or something, but it's ridiculous. Just give it a different number. I'm in like basically a duplex, like it's one house unit above another house unit, and it's still 323 and 325. You don't need to go half, right? Yeah, 1/4 street. I looked for them in Seattle, and there don't appear to be any 1/4s. Yeah, lots of subdivision type action happening. Yeah, it's just like normally the blocks are not so like have so many buildings in them that they really go like 1, 2, 3, 4, but whatever, it happens. That was an attic unit. That's perfect. That makes sense to me. Anyway, for restaurants, it's funny to have a 1/2 address. It's not like they're cramming the restaurant in an attic. Maybe it's some speakeasy they shoved in a basement. Anyway, so continuing. How does this building number regex work? Okay, so let's break it down. This regex is caret square bracket 0-9 square bracket asterisk dash question mark bracket A to Z bracket question mark space parenthesis 1/2 space parenthesis question mark. This looks terrible, right? But it hopefully will make sense if we go through it step by step. So again, we're beginning with caret. So the idea is we know all the building numbers on any normal address. The building number should all come first. So what we want to remove from these strings is going to begin at the beginning of the string. So I'm going to say caret. Then I say bracket 0 to 9. So what brackets are a way to denote sets of things. So what bracket 0 to 9 says is it says look for any numeric digit from 0 to 9. So this is not 0-9, but it's all the numbers 0 to 9, which is every number, right? Every single digit number lies between 0 and 9 for integers, okay? So what we're going to say is we're going to look at the beginning of the string and then find any number. So all of our building numbers, in theory, should begin with a number, okay? So that matches that. The thing is, though, is that we don't just want like to match 5 University Avenue. We need to be able to match something like 5201. What asterisk does is asterisk says match any number of the preceding thing as many times as you want. So this says find a single digit. If I put an asterisk after it, this says find an infinite number of sequential digits, right? And by sequential, I don't mean like 1, 2, 3, 4, 5, but I mean like 5, 5, 4, 7, 8, 9, 10 extending to the moon, and it would match all of them. It doesn't matter how many there are, but it will match all of them, okay? If you want to match a specific number of digits, you can use a more advanced thing, which I could explain in like chat or something later. Okay, so this will match any number of numbers at the beginning of our string. Okay. Then I say dash question mark. So to catch things like 5201-B, I want optionally to be able to match a dash. So this says it's okay if there is a dash there, or not, but don't match any other character other than a dash or whatever comes next. This allows me to optionally look for dashes. Okay? Next, because we have things like 5201-B, we need to be able to locate up to a single character after that dash. Bracket A to Z works exactly like bracket 0 to 9. This says match any letter from A to Z. I don't have an asterisk after it, so I'm only willing to match one of them. If we have a 5201-BC, it's not going to get matched by my expression, and I need to go back and fix it. I put a question mark after it to make it optional. So there might be addresses like 49 University Way, but I also need to be able to optionally get 5201-B with this whole expression. This is a common thing with regular expressions. You'll end up adding a lot of syntax to something to catch some dumb edge case that only happens 1 in 1,000 times, right? I need to be able to catch and deal with it even if it's a really rare thing. So I had to massively complicate this expression. Okay, the next thing we want to match is a space. There's always going to be a space after the number in the address. If it's 55 University Way or 5201-B University Way, there's always a space in between the number and not, so there'll always be a space there. And then, in particular special cases, for those folks who have lived at the 1/2 addresses, I optionally will match a 1/2 and then a space. So this says the entire group needs to be matched. 1/2 space is 1/2 space. The entire thing is in parentheses so that the question mark afterwards says this entire thing must be optional. So this group is all of it goes together. So if it's optional, it's all or nothing for the entire group. Okay, so you can see regular expressions can be pretty complicated. But if you understand each individual component of it, they usually make sense bit by bit. Sometimes if you go to Stack Overflow and you get regular expressions written by people on there, even dissecting it bit by bit will probably make absolutely no sense because they use some really crazy stuff. But these ones are pretty tame, and most of the stuff you're going to want to do is covered by these relatively simple terms. Okay, anyone have questions about this regular expression?
Yeah. If you wanted to catch, like say you lived in somewhere weird, like perhaps Wisconsin that has a 1/2 and also 1/4 or something else like that, could you do parenthesis 1 slash and then like square bracket 0 through 9 square bracket space parenthesis question mark?
Absolutely.
Okay.
Good application. Yeah. That would exactly do it. Another thing you could do is if you knew it was just 2s and 4s, you could do like parenthesis 2 pipe 4 and be 2 or 4. But I like the elegant solution of using the whole, it could be anything, probably not 0. It would be great if it was a divide by 0 address. I want to see that, but it'd probably be, like 1 through 4, 1 through 9. It'd be great if it was 1/9 address. What kind of terrible place do you live when your address is like 1/7? Anyway, yeah, that's exactly what you do. And so you can kind of see how you can just stitch these things together. If you know the building blocks, you can just assemble it and keep making it more complicated. Yeah. Great.
Can I ask, does this handle situations where like a number and then the street name, like they forget the space in between?
So if they've forgotten the space, this will not catch those ones because we've specifically said that there needs to be a space here or here and here. So if there weren't spaces there, that's a special kind of case and we have to figure out a way to fix it. The problem is fixing that actually becomes quite complicated because we've already matched dash any letter over here, that kind of thing. You'd have to figure out how to make it work without accidentally also capturing like the beginning of the street name or something. Luckily, I didn't find any cases in this data set where they forgot the space, but it could happen, in which case you'd probably have to figure out something relatively clever to fix it.
Thanks so much.
Yeah. Okay, so this is kind of cool. And something I want to mention that's nice about these regular expressions. So they're daunting and they look very different from everything else we've done in R. The reason they're kind of like that is that regular expressions are not an R thing at all. The regular expressions I'm teaching here are a generic Unix regular expression. The nice thing about generic Unix things is it probably means everything everywhere uses them too. So if you learn regular expressions in R, you can go and use them in literally every piece of software with pattern matching built into it. It probably uses Unix regular expressions. expressions. It's a POSIX standard. It's an ISO standard for text searching. Every programming language you'll ever go to uses these exact regular expressions, except Perl uses these exact regular expressions for searching for text. You learn this. If you never go on to use R, you can use these in any other programming language you use. So this is one of those general things, kind of like loop syntax. Anywhere you go, these things will treat you well. Okay. So now let's go ahead and remove those street numbers, or at least see how we did. So I'm going to take my restaurant's data. I'm going to mutate a new variable that is the streets only. And the streets only is going to be the result of string replacing in the addresses anything matching my address number pattern with nothing. Okay, so I'm just saying find everything in addresses that matches a pattern and replace it with nothing, which is equivalent to deleting it. There is a shortcut function in stringr called string_remove, which just is string replace with replacement defaulting to this. But I show you string replace because it's more general. Maybe what you actually want to replace it with is spaces or some other text or something like that. You can use string replace for that. Okay. Now I take my restaurant's data, get distinct streets only, and I look at the first 10. We see things like Southwest Avalon Way, Mercer Street, Fairview Avenue North, god damn it, unit 1700A, right? 1700 OA, right? This is not what I want. This is not an actual street. This is a street plus a unit. First Avenue is good. East Valley Highway, 112th Avenue Northeast, number 125 is not good. Northeast Bothell Way. This one, Northwest Gilman Boulevard C-08 has plagued me for a couple of years until I finally remembered to look it up on Google Maps last night when I was going through these slides to figure out what it was. This is not what you would think it is. There is a Northwest Gilman Boulevard. It is in, now I forget which town it's in. It's in the like southeast. There is in a town, C-08 is actually the mall unit number it's in. It's not its street address, but the unit number they rent in the mall is C-08. I have no idea why it's here because it's not their official business address. Might want to deal with that. And there's also Northeast 20th Street, Suite 300. Okay, so this is a case where if we want the streets only, we need to deal with some additional crap. We need to deal with 1700A, number 125, Suite 300. In this example, I didn't deal with C-08 because I wasn't sure if it was building C08 or C-08 when I last wrote these, but you might want to deal with that too. Okay. So let's deal with those next. Okay. So we need to get rid of unit numbers, suite numbers, and all that. So I do here what I'm calling a decent attempt because it's not super thorough. There's a lot of weird stuff that can be tagged onto addresses like this, but I'm going to take a good swing at it here. So what I'm going to say here is if I remove anything that occurs after a £, STE, suite, shop, or unit, it'll be a good jump at it, right? Maybe I should have done APT like apartment, but I didn't actually see any in there because restaurants probably are not usually in apartments, but never know what kind of CDS restaurants are out there. Who knows? Okay. So I have this address unit pattern like this, which is going to be space, $, suite, suite, shop, unit, period, asterisk, $. I'm going to cover it on the next slide what it is. So these examples of things that I want to return in certain ways are First Avenue. I don't want this touched in any way. It should keep the avenue over here. It should leave first alone. Rainier Avenue South, number A. This is one of those addresses that exists. What is a number A? They happen in addresses, but they upset me. So I want to get rid of space number A. Fauntleroy Way Southwest Suite 108. We want to cut off space Suite 108. 4th Avenue number 100C needs to have that chopped off. Northwest 54th Street wants nothing done to it. So I want to say string replace these examples using my pattern above, and the replacement is again nothing. All these addresses come out looking the way they want. So long as all of the weird additions that are on my addresses look like these, they'll be chopped off in the final output. Let's see how it works. So what this says here is all of the things that I want to get rid of, they all begin with a space. They're all something tagged on to the end of the street. So we'll just begin it with a space. Next, we have a group. This group says match any one of these things. £, suite, suite, shop, or unit. any of them. If you had more things to tack on, like apartment or something like that, you can keep adding additional ones here and it would get rid of it. So here's a question. Pound sign is not a meta character? Nope, pound sign is not a meta character. How do you remember whether something is a meta character or not in regular expressions? You don't. You just try and use the thing, and if it doesn't come out with what you expect, it was probably a meta character, put some slashes in front of it. There's a million different meta characters, but it's not like every character on the keyboard. Sometimes it's hard to know. Okay. So yeah, for instance, when I wrote this thing right here, I didn't know it wasn't a meta character. I just did it. It gave me what I wanted. So I'm like, it's not a meta character. Okay. Then the next thing we match, after any of these things, period, asterisk, $. So period is a meta character that says match literally anything. Anything at all in the string is matched by a period. It'll grab anything. If it's a space, a number, a special piece of punctuation, if it is a period, it will match all of those things, okay? Then asterisk, like we used it before, will match whatever thing occurs before the asterisk an infinite number of times, including 0 times, right? So what this basically says is anything that occurs after the pound sign, sweet, shop, or unit, match it no matter how much of it there is, okay? So first it has to match one of these, but after that, it'll take everything up until the end of the string. So if we have unit 49,375,221, it will match all of those numbers after unit. If it is just unit that it ends in, it will match unit and nothing after it, because this matches any character, including nothing, until the end of the string. Okay. So that should get everything I want within the parameters I'm talking about.
Quick question.
Yeah.
If the asterisk goes infinity number of times, why do you have to say until the end of the string? Like, like when it just keep going until the end of the string?
It will keep going to the end of the string. More the reason that I'm matching, there was a good reason for this I had. So there was something about it matching to, yeah, I mean, technically I shouldn't need the end of it here, which makes me kind of want to remove it and see if it messes something up. I feel like I added it for a reason, but it should go to the end up to there. I'm wondering if for some reason it needs to be anchored to the back end of the string instead of allowing it to match to the front, but I can't think of a reason why that would be the case, because this should match everything. So it's probably extraneous. And if I remember, I'll go check, and if it is truly extraneous, I'll just remove it from the next iteration of these slides. So you're probably right. I think it is extraneous, but it doesn't mess anything up, hopefully. Good find. Yeah. So this is an example where I'll construct it, it works, and I just leave it alone because it works. It might have stuff that's unnecessary in it, but it does work. Though to be proper, I should not show people extraneous things. So thanks for pointing it out. Okay. So let's go ahead and do it. So I say, take the restaurant's data, then mutate, so street only is equal to, again, string trim in case we have any extraneous spaces, the result of string replacing our street only variable by that pattern, replacing with nothing. I can then say, look at restaurants, distinct streets. I do the first 11 because it fits nicely on this slide. And we see we have Southwest Avalon Way, Mercer Street, Fairview. We have all these down except for this Northwest Gilman Boulevard C08 because I didn't change it after I checked this out on Google Maps manually myself last night, which is how the real data analysis procedure would work. You'd find things that don't fit your pattern and make sure you should be removing them, right? Okay. If this was a serious project and I was going to be doing analytics on this or something, I would probably then figure out a way to remove the C08. If it was the only one like it in the entire data set, I would just manually match C08, but maybe there's other ones like it. Okay. So, any questions about that? And I'm just horking coffee down today. Okay. I'm already out. I'm going to die. Okay. So, now we can get to the question that I had that sort of initiated all of this string removing, right? I want to figure out where danger lurks in King County or especially in the city of Seattle. So what I'm going to do is I'm just going to get the number of 45 plus point inspections that occurred on every street in my data, okay? 45 plus is a lot of health code violations, right? That's a place that probably should have been shut down immediately. Anyway, what I'm going to do is I'm going to take my restaurant's data. I'm going to filter it down to only inspections of a score 45 or higher, get the distinct observations on business ID, date, inspection score, and street. So by doing this at business ID and date, I could have the same restaurant repeated multiple times if they had multiple inspections above 45. I'm then going to count the number of observations on each street, arrange descending, and get head the first 5. So the answer to where does danger lurk in Seattle? Danger lurks, of course, where all of the delicious food lurks in Seattle, right? So University Way Northeast has 108 places. Yeah, well, my office is in Savory Hall, so I'm probably not going to stop eating at University Way Northeast, right? That's right outside of the school. I'm going to keep eating there. South Jackson Street is the International District. I'm not going to stop eating down there. That shit is delicious. Pacific Highway South, oh, it's Aurora. There's so much good food up Aurora. I'm not going to stop going to like my Indonesian restaurants. Northeast 24th Street is kind of like on 24th, cuts off up there and then northeast of where I'm at. Rainier Avenue South, of course, is in Southeast Seattle, Southeast Seattle. There's tons of good food there, okay? So the answer is the delicious food might poison me and I'm not going to stop eating it. Okay, but we've learned important lessons. Okay. So on to some other things. So something you might want to do, this is a random slide I toss in because it's a procedure that when I'm working in the consulting center at Caesar, I get a lot of people coming in for string separation questions. So I just insert it in here to head you off for later. Sometimes what you want to do is take some sort of text string and divide it into 2 or more separate string vectors based on something, maybe by spaces or something like that. Back in week 5, we used separate to do this with minutes and seconds of songs, but you can do it more advanced and with more dividers using string split, okay? The idea with string split is you can give it a regular expression and it will split everything before and after the regular expression into multiple vectors, okay? The thing is, though, is it returns it as a list because there could be an arbitrary number of things you're splitting by. So just know that if you want to come back as a list, use string split. If you want to come back as a matrix, you can use string split fixed, but this assumes an even number of separators across everything. An application of this is in these restaurants' data, the violation descriptions are a number as the code violation followed by the actual written description of what that code violation is. Maybe I only care about the written description. I could say, let's split the violation descriptions by space dash space, which is the divider they use in the actual data. And I want it to come into 2 pieces as the result. This gets rid of all the numbers over here and just gives me things like proper shell stock ID, wild mushroom ID, parasite destruction procedures for fish. So this is a place that isn't identifying the things that you eat very well or doesn't tell people, you know, they don't have a license to have the things that they have. Okay. So something that I added last night to this to buffer this lecture out, because it always finishes about 20 minutes early, is this little section. So something you might want to do, and I've had a fair number of students come to me again at the Caesar Consulting Center doing something like this. Maybe you have a report or a website where you need it to dynamically generate sentences or paragraphs of text based on stuff that's in your data. There's actually a really good example of this the New York Times did a while back, where they wrote this article that reconstructs all of the text in an entire article, I forget what the actual topic was, depending on what state you pick in the United States. You go and click into Oregon, kind of where I'm from, and the whole thing gets repopulated with information about Oregon. It changes the tone of the article. It says all sorts of stuff. You can do dynamic sort of reporting like that, but to do it, you actually need something that will stitch all of this stuff together properly into the text. If you want to do this in the data directly and not with inline R calls, you might use something like what I'm going to show you here. So to do this, I need to load up the Lubridate package because I'm going to be working with dates a little bit. And then I'm going to prep some recent scores in my data. So the recent scores are just going to be the most recent inspection scores from restaurants in the data. To do this, I say, take my restaurant's data, select the columns I care about, which is the name, address, city, inspection score, and inspection date. I filter to inspection score is not missing because there's a fair number of missing inspection scores. I don't know the exact reason for this. It might be that some of these are supposed to be zeros, or some of them where inspections haven't happened or they didn't report. I'm not sure. I group on the name of the restaurant. I arrange it in descending inspection scores, and then I slice one. Slice one gives you only the first observation within each group. So if I arrange by descending inspection score and slice one, this gives me the row with the worst inspection score. That is the highest inspection score for each restaurant. I ungroup my data, and then I'm going to mutate the name, address, and city columns to be title case. So I'm going to be printing text out to the console. I don't want it to be all capitals. I instead want my names, addresses, and cities to have capitals at the beginning of each word. String to title will do that. It's title case. I then say mutate inspection date is using lubridate's MDY. I take my inspection date, which is in month, day, year format, and change it into a date object using MDY. And then I'm only going to pull out a random sample of 3 restaurants to use as examples. So here's a great question. Why do I ungroup? So because I did group by name and slice one, this is not a summarize command, so my data remains grouped. I don't want my operations that occur after this to occur within the name group. I actually want it to occur across the entire data. These ones will work perfectly fine, but the commands I'm going to use in the later examples, I don't want to happen within the individual restaurant. I want them to happen across the entire set of data. Another thing is that generally, if I group on something and do an operation that doesn't remove the grouping, I just always, as a practice, remove the groups manually just to make sure I don't forget they're grouped later and do something dumb. So it's a kind of a good thing to just remove your grouping structures if you're not planning to use them. Okay, so I could say use the paste function with lots of arguments to assemble a sentence out of all of the individual variables and some strings. I'm going to load up the scales library, which is going to do something handy I'm going to show in a second. What it is it allows me to add, like, if I want to say the 3rd of May and the 5th of May and not manually add RD and TH to the appropriate numbers, I can use the ordinal function in scales. It will look at a number and put the appropriate suffix on it to make a proper readable word. Okay, anyway, so what I'm gonna do is I'm gonna take my recent scores data and I'm gonna mutate a new text description column. This is going to be the result of pasting together all sorts of junk. I'm going to paste together the name of the restaurant and say it is located at this address in that city, and it received a score of inspection score on the date of the inspection. Month of inspection date will return the numeric month. If I add label equals true, it will by default give you a 3-letter abbreviation of the month. May will just stay May, but July will be JUL. Unless I say abbreviation equals false, then it gives me the whole month. January spelled out, February spelled out, whatever. So this gives me the month fully spelled out. Then I'm going to say, I want to, and this is where it gets annoying, paste together the ordinal day of the inspection date. So this is going to be the day of inspection date. If it was inspected on the 3rd, it would be the number 3. If I say ordinal 3, it's going to be 3RD, the 3rd, but I want a comma after it, so I paste a comma onto it here, paste a comma on, and then I also add on year inspection date with a period. Year just extracts the numeric inspection date. Then I select my text description column I've created, and this is what I get. Supreme Bean again is located at 14424 M Baum Boulevard, Southwest in Burien. And if this didn't get cut off because there's no automatic line breaks, it received this inspection score, blah, 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 at this inspection date. The cool thing about this is this would do it for every single restaurant at every single address at every inspection date in my entire data set, right? If for some reason I need to be able to dynamically spit out sentences like this, like I was programming a web front end or something, this would generate valid sentences for all 280 whatever thousand rows in my data set. right? Flapjack's Waffle House is located here, and this was its inspection score, okay? This is one way that you could stitch text together, okay? Paste is sort of a primitive way to do this, though. We could move on to Paste's more sophisticated, better tasting sibling, the glue package, okay? So rather than pasting things, we can play with glue. So string_glue is a version of Paste which uses the tidyverse glue package. Glue is a flexible framework for stitching text together that's a little less awkward than giving Paste a million arguments, okay? The way glue works is a paradigm you have not seen yet in this class. What it does is you give it all strings. You give it nothing but text, except you give variables in R code you want to use inside squiggly brackets, and it disassembles this thing and runs all the code for you without you having to do something like a variable name, a string, a variable name, a string, a variable name, a string, right? Instead, you just give it a whole bunch of strings and it figures out how to stitch them together. So what this is going to do here is we're going to create a vector called score text, because I'm going to do something fun with it on the next slide, which is equal to recent scores mutate a text description, which is the result of gluing together a bunch of strings. What we're going to glue together is this. We're going to say name is located at address in city. So what glue is going to do is it's going to go find the value of the name variable, put it here, then say is located at space, the value of the address variable, space in the value of city. And I do this is one string, and then I do a comma. The only reason I'm doing this is to make it readable. The thing about glue is it's going to stitch all of these together no matter what way you organize it. So you can just write as much as fits on each line and break it up however you want for your convenience. This is something kind of nice about glue. It's flexible. Then we're going to say and received a score of inspection score on month. This is the exact same R code as on the previous slide, the exact same R code as the previous slide. You'll notice here, though, that instead of saying inspection date, I say when. Instead of inspection date, I always say when. This is a cool thing that glue can do. Glue can create temporary variables just inside of glue, so you don't have to type out long variable names. I say here, any place you find when in this entire glue statement, put the inspection date variable there. This makes this all more readable by saving me a whole bunch of horizontal space, okay? The result is exactly the same as the paste version, but this is often easier to write because it's a single sort of string that looks like a paragraph you might write out. You just specify variables like this. If you find this less convenient than the paste, you don't have to use it. If you find it more convenient, it will do everything paste will do, and technically more if you delve into it. There's a link here to the website for glue. It can do some neat stuff. Okay, but this says the exact same thing as before. Flapjack's Waffle House is located here, blah, 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 blah. The annoying thing about this is because of the way R prints out text, it doesn't do line breaks in the console, so it's hard to read. This would be perfectly fine if you pulled this out as inline text in your markdown. It would do the line breaks and stuff. But if what you actually want is this text displayed in your console, we could add line breaks to it. So there's some functions in stringr and sort of just general text in R to add line breaks. There is a string wrap function and the \n meta character for adding line breaks, okay? So string wrap is a function in stringr that will add a line break in text automatically at any interval of characters. So if you want to print something to the console and you want every line to be 70 characters wide, I can say string wrap 70, and after 70 characters have occurred, it will add a \n, and that will do a line break. \n on things printed to the console will create a line break, okay? It will not create a line break in HTML or in LaTeX, but it will do it in console prints. If you want to add a line break in HTML or you want to add it in that, you'll have to do it in a slightly different way. Actually, string wrap will work, however, in tables produced by Pander, I think, and maybe GT. So some packages can handle it. It will also definitely, /n is the line break character in ggplot. So if you want to regularly like create paragraphs in ggplots, this is the way to do it. So what I do is I take my score text, which was a data frame. I'm going to pull out just those text descriptions so they're a vector. I'm going to say string wrap them so their width is 70. And then I want to paste on to each of those elements \n/n. This is going to make 2 line breaks after each one of them. It's going to kind of make a paragraph break. And then I'm going to concatenate them. Cat just combines things together and prints them out as one big text vector in your console. Now we can actually see what the sentences I generated in the last 2 slides look like. Supreme Bean again is located at 14424 Ambom Boulevard Southwest in Burien and received a score of 10 on January 24th, 2017. So this is human readable, dynamically generated text using a few sort of string functions we've used in stringr. Okay? Most of you probably won't have a case to use this exact sort of thing, but maybe you will, and this will show you how to do it. And it's kind of fun to play with string. Okay. So, last thing I want to say are a few other useful stringr functions which I don't have slides for, but someday I'll probably add to this lecture when I get around to it. String pad is the opposite of string trim. What string pad will do is you give it a string, a total width you want each one to be, a side you want to add stuff to, and what you want to add to it, and it will make the string a minimum of this width, and it will add whatever you say pad to the side you pick until it is that width. If you get something like zip codes that are in the far east that have leading zeros, load them in as numeric and they lose their zeros, you could say string pad my zip codes, the width should be 5, I want to add stuff to the left side and I want to pad it with zeros. That would make sure they're all length 5 and any zeros get added back in. It's an operation I do often with national zip codes. String subset will take a string and a pattern and it will return all elements that contain matches of the pattern. So this is like string detect, finds trues and falses, but instead of returning a true and a false, it matches something and then returns the entire string and not just the things it matched. So this isn't like string extract. For this one, it would give you the entire thing it matched to. This is good for creating variables and mutate. String which will return numeric indices of elements that match the pattern. So this is like string detect, but instead of returning a vector of trues and falses, it returns the numeric indices of whatever it was matched to. String replace all is the same as string replace, but string replace will only do one replacement in each string when you call on it. If you have multiple things you want to replace, like bad punctuation or something, use string replace all, and it will do multiple replacements within each string. And then I did mention string squish earlier. This will trim spaces on the outside of a string and also replace duplicate spaces on the inside of it. Okay. So that's everything I've got for today. The next thing, and so it says here that homework 6 part 2 is due next week. I'm just going to bump it out a week. I have to go and adjust that in Canvas, but let's just make the homework due not on Monday, but on a week from Monday. Take a break or work on it in the meantime if you want. The lab will still be the Monday preceding when it is due. Okay, anyone have any questions? Nada. Yeah, I'm tired too. Okay, cool. Good to see everybody. Have lab not Monday, but the next Monday. Hit me with questions and stuff like that. I'll try and get, I meant to have grades posted today, but I haven't gotten around to it. I will post the grades for the previous ones. Otherwise, we're good. Hit me up on Slack or email if you need anything. Have a good long weekend. Not that time or holidays matter anymore.